Please wait. And we're on.
Okay. All right. Well, welcome to Bite of Physics number 75, third episode of the Stellar Aberration series. I'm John Mallinckrodt, your host for Bite of Physics, and welcome to everybody who's come. And we're going to get started on this. The slides are up there at the top of the page, and you'll see on the first page there the links to all of my bites of physics and a growing collection of public documents that you might be interested in if you have no life. So there you go. Let's move right into a little review. First few slides here are a review. Last couple of weeks, we were talking about Bradley's explanation. I just realized there of parallax. I'm going to change that. That should say stellar aberration. That was the point. Bradley was looking for parallax, but he found stellar aberration, and we spent some time in the first episode talking about a little review. The first few slides here, a review. Parallax. Last couple of weeks, we were talking about Bradley's explanation. His explanation of stellar aberration. I'm going to change that. Was basically that particles of starlight are raining down on the Earth. Bradley was looking for parallax, but he found stellar aberration, and we spent some time in the first episode Newton. A little review. The first few slides here, a review. The authority of last couple of years talking about Bradley's explanation. So his explanation aberration is just a result of moving was basically rain particles starlight raining down on the Earth. Bradley was looking for rain, but he found stellar aberration. When you move in the way starlight, you have to tilt your telescope forward in order that the light travels straight down the tube. It's a very small angle. He was measuring angles of 20 arc seconds, which is 1/3 of a minute of degree, where a minute of arc, where a minute of arc is a 60th of a degree. So we're talking here about something like a 200th of a degree difference between the direction of the star from one time of year to the other as the Earth moves in one direction and then another. On slide 3, just to review, if you think of this as rain, you can think about, last week we went through these 3 observers, a blue observer, a green observer, a red observer, all moving relative to each other, and showed how they would see light both moving at different angles and, of course, different velocities, which is perfectly fine since they're particles. They can move at any speed they want. The only real question was, why did they always seem to move so fast, maybe? But we talked about a case, just to make the angles a little more reasonable, we talked about a case where the light would be traveling at 12 miles per hour, so that normal speeds for normal people of 5 miles per hour and 9 miles per hour could make a really noticeable difference both in the angle and the speed. And so we went through this and we asked the question, and we saw that we could see it from each person's point of view. Each person understood why the other person was saying what they saw because of the simplicity of the so-called Galilean transformation, Galilean relativity. The blue guy understands that the green guy sees the light kind of angling down toward him, and that the red guy sees it angling down toward him because of their relative velocities, and all that makes sense. So the only question is who is right? Which one is right about the direction of the star? And the answer in Galilean relativity is really that they all are. All of them are literally seeing the star where it was when the light that they're now seeing was emitted. And because they're in different reference frames, that all sorts out differently. But the lesson is that you can think of it in terms of moving through a rain, or you can think of it in terms of just light coming straight to you from a star or where it was when it emitted that light. Either way, you get the same answer, you get the right answer. And it doesn't matter, except that in the particle so the lesson is that you can think really of it in terms of moving through a rain, to think or about you can think of it in terms of just light coming straight to you from a star or where it was when it emitted that light. That way, either way, you get the same answer. You get the right answer that you're moving, and it doesn't matter. There's the suggestion in the particle you are really moving. Think of it in terms of moving through a rain. Or you can think of Galilean relativity. Nobody somebody has to say they're moving, and if you actually decide that you're moving, then you're somehow deciding that you're moving relative to a more important reference frame than yours, and there is no more important reference frame than yours. So the whole moving through a rain thing just isn't the right way to think about it in the particle view, even though it gives the right answer. And that'll be a recurring theme. We're going to see it turns around exactly when we go to the wave view. It's just the other way around, and that's what we'll be doing in the rest of today. So I want to just quick review of the slow rise of the wave theory, what the critical points were, and that's what we'll do on slide 5. In the mid 1600s, this guy Grimaldi made some early and pretty primitive observations of diffraction, the fact that light kind of bends sometimes around the edges of obstacles. That was a funny thing for particles to do. There was some understanding of refraction, the fact that when light travels through a prism or something like that, it bends. And there were some pretty good ideas about how you might make particles do something like that. But it wasn't clear why light just traveling through the air should bend around obstacles. That's a funny thing to do. And then a bit later, Bartholinus was the first to observe so-called double refraction in calcite, which suggested, which ultimately would be explained in terms of polarization effects, but was also, once again, a hard thing to explain in terms of particles. So those were early things. Huygens, just around the time of Newton, around 1690, proposed a very primitive and essentially qualitative wave theory of light using Huygens wavelets. If you might have heard about that, we've had a couple of previous bites of physics on that I'm linking there: a refraction bite of physics and a diffraction bite of physics. And he suggested polarization as an explanation for double refraction that Bartholinus had first observed. Still, and nevertheless, through the 1700s, the corpuscular theory reigned, bolstered especially by the dominance of Newton. It's hard to underestimate how much the admiration of Newton in the 1700s kind of kept the corpuscular theory alive, despite these little things that were pretty hard to explain. But then things 100 years later, we're now talking about the beginning of the 1800s, 19th century, Thomas Young made a careful study of double slit interference, something that particle theory just really did not explain, and came up with a pretty good explanation of that Fresnel then really put the final touches on by taking Huygens' theory and putting it on a very firm mathematical basis involving integral calculus and working out how waves both diffract, refract, reflect. All of these, everything that had been seen was explained very nicely this way. And because of his proposal that light be a transverse wave, allowed the explanation of these polarization effects, that the wave can, like a wave on a string, can be vibrating either up and down or side to side. Same idea with light. Waves that are transverse are waves where the waving is going on perpendicular to the direction of propagation. And so Fresnel suggested that these light waves must be transverse waves so that they could have these polarization effects. This was all in the context, by the way, of a competition put on by the French Academy of Sciences for a good new theory of light. Fresnel put his theory forward, and Poisson, who was a dedicated Newtonian corpuscularist, was looking for some way to cut Fresnel down. So he noted that Fresnel's theory predicts a very counterintuitive white spot of light right at the center of a shadow cast by a disk. If you had a perfectly circular disk, Fresnel's theory suggested that there should be a white spot, a light spot, right at the center of that shadow. And Poisson really thought he had put the kibosh on Fresnel for that. But Arago quickly went out experimentally and saw that there was a white spot at the center of the shadow of a disk. And probably if there was one thing that created the avalanche to the wave theory, that was probably it, this Poisson spot, or Arago's spot as it is variously called, was really a swift kick to the corpuscularists. And within the next 10 years, pretty much the corpuscle theory had gone away. Fresnel's theory tackled things one by one, explaining them nearly perfectly. And so that was pretty much the end of that. Some 10 to 20 years later, some experiments in electricity and magnetism started suggesting a relationship between electricity and magnetism and light. And that culminated in Maxwell in 1865 publishing his Maxwell's equations, from which we get an actual equation for electromagnetic waves, and the remarkable coincidence that those waves are predicted to travel at the speed that was then known to be the speed of light. That seemed like that couldn't be a coincidence. And so that really firmly established light not only as a wave, but as an electromagnetic wave, and as a transverse electromagnetic wave, as Fresnel had suggested. So a little history of that. And I want to say, in preparing for this, I've found it really useful. I'm a real novice in AI, but I've been having some very productive conversations with Gemini recently, and it's been fun to, to kind of tweak my understanding of things that I am starting to appreciate the interrelationships between. So a lot of this does come from those conversations. I've had to occasionally kind of point out to Gemini that this doesn't really make sense, and then of course you get a very nice apology. It's funny how endearing it is when an AI says, "Oh, you're absolutely right. I apologize. I'm so sorry." That really actually, it's astonishing to me that I find that endearing. It actually makes me want to keep talking to them. Okay, let me stop there for a second. Any comments on that or the endearing features of AI before we go on to the next slide?
Are you going to tell us more about that bright spot in the middle of the disk, or is this homework for home?
Yeah, I'm not. I could. It's maybe I will see. It's not that difficult to understand if you think about the net result of little circular annular rings of light outside the disk. Let me just give you a hint. Some of you will be able to follow this hint. And if not, maybe I will try to say something about it. But if you think about, basically Fresnel's theory says you take all the parts of that plane that the disk is in that aren't covered, and then you propagate the light from each one of those points. This is kind of the Huygens wavelet idea. You take every point that's not blocked out, and you add the contributions all up at any point you want. So an easy way to do that is to just think about that unblocked portion as a whole bunch of infinitesimal annular rings, because each one of those rings will have the same phase relationship at the center of the shadow. And then you think about what happens when you add those all up, and you can see that if the depending on the details of the size of the disk and the wavelength, sometimes you won't get the spot, but oftentimes, about 50% of the time you will, and 50% of the time you won't, depending on phase relationships. So if you think about just integrating over those annular rings, that's what Poisson did to show that you should get a white spot. And I'll save the rest for later. Good question, though, Shamash. All right, let's go on to slide 6. So the pros and cons, it's also worth just really appreciating that even in the early 1800s when we started to get this, there's still some pros and cons. The pros of the wave theory is that it provides a reason for light to have a speed. If light is a wave, then the speed of light is the speed of those waves, just like it is for sound, just like it is for waves on water, just like it is for waves on a string. And wave speed always depends on some competition between the stiffness of the medium and the inertial, how much mass the medium has, something like that. It at least provides a reason for light to have a speed, so that's cool. But most important and eventually decisive, it accounts for refraction, interference, diffraction, polarization effects, all of these things that particle theory just really can't. That was ultimately the decisive thing. But there are a lot of cons. Number one, it was just counterintuitive at the time. People thought about light and it was just so obviously particles. It traveled in straight lines like particles do. Um, it just was counterintuitive. And it's funny to that's another one of those things where I have to put myself in their brains. It's hard for me to think of wave light as being counterintuitive because I know so much about why we think that. But if you don't know that, it really is a counterintuitive idea. Light just seems like particles. Reflection and general straight line propagation is just easier to explain with particles. Particles bounce off things, pool ball type effect, etc. So that just kind of makes sense. It's a little trickier, as we'll see, to explain stellar aberration with a wave theory. We'll see that this time. But the most important reason for continued skepticism really was the fact that these waves, if they're waves, they are incredibly fast. And incredibly fast waves require a medium. First of all, waves require a medium to travel through. And this medium would have to be highly rigid, incredibly rigid, because these waves travel really fast. Like sound waves in steel travel much faster than sound waves in air because steel's just so rigid. This would have to be really rigid and incredibly tenuous because we don't feel ourselves moving through it. So it's at once incredibly rigid and so tenuous that we don't notice it at all. That just really didn't make sense. So that was a very hard pill to swallow. And then in addition, it suggests a violation of Galilean relativity. It provides a preferred absolute rest frame for observations of light. And it provides a way for you to determine your own absolute velocity with respect to that preferred rest frame. Now, you may or may not think that that's a violation of Galilean relativity. You can have waves in water without violating Galilean relativity, but it seems a little more like talking about a universal rest frame filling the universe when you start talking about light from distant stars, etc. And the rest of this presentation is going to focus on that whole Galilean relativity wave, whether you think of the light as being a rain coming from afar, or simply light coming straight to you from an object. So let's on slide 7. Well, let me stop there for a second. Just pause anyway.
Yeah,
Any comments?
can I
Yeah,
just
go
squeeze
ahead.
this comment very
Hmm.
quickly? This probably is one of the textbook examples of what we were talking about during the philosophy rooms. So they got to this ether rule and the properties of the medium and that it needs to be very. All of this was just because we've seen waves before and we've assumed that what we're dealing with is exactly the same. This is an error of induction. Probably this is one of the best examples that I didn't give and I should have.
Yeah. Yeah, no, that's a good point. I mean, it's really just saying, well, we know what waves are like, so this will have to be like that as well. And I think probably some appreciated the fact, because I think probably the most important thing for physicists of the time, we sometimes talk about the 1800s as a time when people were trying to figure out whether or not there was an ether. That's not what they were doing. They knew there was an ether. There had to be an ether. The only question was, why are we
Yeah,
having so much trouble detecting it? Yeah. So so we'll go on from there.
yeah.
Yeah,
Sorry.
yeah. CM, go ahead.
Well, I was just gonna
Welcome.
mention. Yeah, it was because up to that point, let's say the mid to late 1800s. What's it called? every single wave phenomenon ever observed, including light waves. I mean, not except for like, besides that, water waves, sound waves, pressure waves, every kind of wave always required a medium for it to propagate through. And so that, and they were just discovering, well, I mean, they were just finally doing experiments on light, electromagnetic radiation, photons. And so
Well, we're not.
they just assumed the same
I
thing.
I
That's
do
where the ether
want
came
to
from.
I do need to kind of jump on that. Photons were the furthest thing from their minds, right? Unless you want to talk about Newtonian theory being corpuscles being photons.
Yeah,
I'm
that's
really trying
exactly
to
what they
do
are.
this in a
But
historical frame, so we don't want to introduce ideas before their time. But as you
no,
say,
no,
it's
but they,
certainly the case. It's certainly the case that that waves obviously need a medium because a wave is
or we
nothing
thought,
but
yeah,
the motion of that medium, right? That's what it is, and so they had no question about that. Go ahead. Just
yeah,
take another 30 seconds or something.
yeah. So, or we thought that every wave phenomenon needed a medium for it to propagate through. They didn't understand at the time, and that's why they were looking for the ether. That yeah, that electromagnetic waves did not require a medium.
Yeah, well, once again, I don't really want to jump ahead. I don't want to really even mention things that we haven't gotten to yet. All
I
we're
mean,
really doing
so
is
are we going back?
establishing
Are we
here.
going to the Michelson Morley
Oh, we're
experiment?
way back. We're 100 years before Michelson and Morley here. We're
Okay.
talking about, yeah, early 1800s, and we'll get to that next time, or either next week or the time after that, which will definitely be the last one. If we There'll be one or two more in this series, so we will get to that. So let's look at slide 7, where I just show, for instance, what things look like for a light source that is at rest in this ether. If I have a light source that's at rest in the ether, then it's putting out waves, and I'm indicating these waves now with what are called wave fronts. Each one of those circles can be thought of maybe as if these were water waves, those might be the high points of the water. So there'd be a circular high point, a circular collection of points that are all high. And then in between that and the next circle, there'd be a low point, which I haven't shown. And then there's another high point. So each one of those circles, just think of them as a high point. The distance between each one of those circles would be what we call the wavelength, the distance from one point in the wave to the next place in the wave where it has the same phase is the thing we call it. So the phase of the wave could be a peak, and then the next peak, and then the next peak. That's a full cycle. That's one cycle, 360 degrees of waving, or 2 pi radians of waving, all those at one time of those wave fronts. And if I animated this, all of those wave fronts would move outward from the fixed source as maintaining their concentric circular nature, and just getting bigger and bigger with the ones in the middle being replaced by new ones, right? The light is constantly putting out new waves. So this whole thing just expands outward. I've got some, what we would call rays of light. Rays of light represent kind of the direction that the light is moving at any point. It's the direction that the wave front is moving at each one of those points. So that's what it would look like in the frame of the ether for a source that's not moving through the ether. That's important. We're going to talk in a moment about what it looks like if the source itself moves through the ether. But for right now, it's a source that's at rest with respect to the ether. And then I've just shown a bunch of observers, some blue observers who are at rest with respect to the ether, and therefore just see these waves washing over them. And some red guys who are moving through the ether, and therefore will have a little more complex view of the light. They're not just sitting there watching the light wash over them, their motion is going to cause some differences as well. It's going to cause aberration, in fact. So we'll talk about that. Okay, next slide maybe, or comments. Okay, let's go on to slide 8. This is what a moving observer does not see. Now, I want to talk about what that looks like for a moving observer. And I'm showed a couple things, one of which on the left there is not what a moving observer sees. You may remember that when we talked about the particle theory of light, what happens is if you're a moving observer, then you have that, all that really means is you're moving relative to the source. And so you have every right to just think of the source as moving. And as the source moves, it emits particles from places that move further and further to the left. So you're going to get a kind of a skewed thing like that picture on the left, if you thought that was the case in the wave situation, but it's not. If you're a moving observer, it doesn't change the fact that all of those wave fronts are concentric circles. They can't bunch up like that. And so what you're going to see is really what's shown on the right. You're just going to see a bunch of concentric circles moving outward and being replaced by new ones as they move outward, with the whole pattern moving to the left. Right, so the entire pattern moves to the left as it expands radially, remaining concentric circles. That's what you would see. Now, notice in this picture, I've put a little arrow on the observer down there, kind of indicating that he's moving. But I probably shouldn't have done that. I want to be clear that this is what that observer sees in his rest frame. In his rest frame, there's an ether wind that carries the whole thing to the left. And this would be just like what you would see if you were standing next to a river and somebody moved with the river, dipping their finger into the river. Every half second or something. If you dip your finger into a lake every half second, you create a bunch of concentric circles coming out. And if you move with a river and do the same thing, you also create a bunch of concentric circles. It's just that they now are being carried downstream by the river. And so that's what you standing by the bank would see, because you are not in the preferred frame for those water waves. You are now actually moving with respect to that medium, more properly, with respect to the medium, which is itself to be kind of considered the preferred or rest frame. So comments, questions on that one? That one
Very
takes a little
quickly,
thinking. Yeah.
Yeah, of course, the moving person would perceive the shape the same, but they would not calculate the speed of the wave to be the same from their frame of reference. Because
That's
if
right.
they are moving radially out with the same speed, the speed of the wave will be zero.
That's right. Exactly. That's right. So, and we that's another important point, just to remember, we're not to relativity yet, right? We don't know about any of that. These waves clearly will have even though they do now have a velocity, that velocity is the velocity that they have in that preferred reference frame. If you move toward the source, you're going to see those things moving faster. And if you move away from it, you're going to see them moving slower. So yeah, no, that's exactly right. Okay, move on to slide 9. In slide 9 now, I want to now talk about, let's observe a light source which is itself moving. So now we have a light source that is moving through the ether. So this would be like either on a lake, you could dip your finger into the lake from positions that are gradually moving in some direction. Then you would create expanding circles from those points. But since those points are moving relative to the water, those circles won't be concentric. Or simply stand by a river as it moves by and dip your finger in it while it moves by. That would be a source of waves in the water that is moving relative to the water, moving upstream relative to the water and doing the same thing. So now you really are creating a pattern that looks like this, and that's what the pattern looks like, no matter what reference frame you're in. If you're in the frame of the ether, each one of those waves continues to expand out perfectly from the place where it was created. So that's not, the pattern doesn't move, but it does expand out. And as the source moves to the right, of course, the kind of focal point of the pattern does move to the right. But at any given point, there will be a wave like the outermost wave that will also now be it will be further to the right, but the wave that it has become will be still centered on the same place that it came from. Boy, that was a bollocksed up sentence. Sorry if I didn't say that very well. Each one of those waves will continue to expand from its center, but it will be replaced by one of the same size that's a little to the right, and that will continue. So the whole pattern both moves to the right while the individual waves are simply expanding from their centers. That takes a little thinking about, so don't mind you taking a moment to think about it. The next
This is
slide,
the
go ahead.
this
Yeah,
is the scenario that happens with the sonic boom, right? So the source is moving, the source of the wave is moving, and then it hits that boundary of all those waves kind of collecting together.
that's right. So and you can see this, yeah. So you see that with planes. If a plane moves forward, effectively, it's a little complicated because it's a, it's not like it's not really a sound thing, but as the plane moves closer and closer to the speed of the mechanical disturbances in the air that it's creating, those waves on the front side are bunching up to the point where now they're all on top of each other, creating a shock wave. And when the object actually moves faster than the wave speed, then you've got, of course, nothing out in front and simply all of those waves. You can draw a picture just like that with circles now that are centered on points that move faster than the circles expand, and you'll see that you create kind of a cone shock wave like you get with planes. It's tempting always when you talk about this to talk about boats. Boats create these V waves like a shock wave, but the interesting thing is that a boat will create a V wave no matter how fast it travels. You'll see a V wave, and that V wave will be essentially the same angle. That's a complicated thing. We've talked about that before, and I don't think I have done a bite of physics on that yet. I have to do that one of these days. But I did want to say, and I didn't mention it here, that a stationary observer in this frame, in the ether frame, a stationary observer to the right of the source will see waves coming by him more quickly. Right? They're all traveling at the same speed, and so those waves will come by him more quickly than will an observer on the left, to the left of the source, because that observer will see the waves traveling once again at the same speed. Both observers will see the waves traveling at the same speed, but the wave fronts have to travel further to get, one wave front passes the observer to the left, and then it takes a little longer for the next wave front to get to him just because they're further apart. And that's the Doppler effect. When a train goes by, that whole kind of thing is a result of. Did I do that pretty well? I've got a pretty good Doppler impression. Higher frequency as it's coming toward you than when it moves away from you. So we've been joined by a couple people on stage. Let's see if they have questions right now or just want to hang out with the cool kids. Jesse, go ahead. Okay.
Sorry about that. I was
That's okay.
caught me in the moment. I was trying to send a message.
Oh, okay. Sorry.
Yeah, I just jumped in. I was actually on Machine Learning Street Talk Discord for a little bit, and there was a philosophy of science conversation happening. I don't know what happened to it. So what you're talking about is like kind of like before getting to relativity.
That's right.
Was first formulated by well, not necessarily just Einstein. I forget his name. What was his name? That was
We'll get there. Yeah, let's not worry too much about that. I will just maybe reset the room a little bit and make clear that in this series we're kind of taking a historical approach. We all centered on the observations of stellar aberration, and we've talked about the particle theory of light that reigned up until the early 1800s. And now we're just kind of talking about the introduction, the reasons for thinking that light is a wave, and the struggling that people went through to try to understand the nature of light as a wave. And we will definitely get to the good stuff next week or the week after. But this is good stuff too. Yeah. Anyway, but you're welcome here. If you have another question about that, that's fine, or comment, that's fine also. Let's see if Kevin wants to say something now, or if he just wants to hang with the cool kids.
Oh yeah,
Go ahead,
yeah.
Kevin.
You actually. Oh, hi. Good morning. You actually caught me too. My hands are literally full. I haven't had coffee or anything.
Oh man, I know that problem.
Oh man. Yeah. So this messes me up. But just you were talking about boats and stuff. So I would just throw it. At the back of the boats. You get the effect with the bubbles.
Right.
Make the light. Yeah. Okay. I just wanted to throw that in as well.
Yeah. Okay. Yeah. Good. There's all sorts of good wave things. I've done some wave bites of physics before on diffraction and interference and probably some other things. I don't know, but I need to do one day about boats. I think I will try to put that in the hopper. So let's move on to slide 10, where I want to get a little more specific about what a stationary observer is going to see in the case of, and when I say stationary, of course, I mean, you know what I mean now, stationary with respect to the ether. So this light source is moving to the right through the ether, and now we have 4 stationary observers, and I've put them purposefully at equal distances at the same kind of level, if you want. They're along a line parallel to the direction of motion of the source, and they're spaced equally. And each one of them is just stationary. They're seeing these waves pass over them. And the question is, well, so what do they see? So let's just look really carefully at observer 1. Observer 1 right now is seeing a wave front moving mostly to the right, but a little bit downward. And so if we interpret that in terms of where he sees the source, he's going to see the source in the opposite of that direction. So I've drawn a green arrow back to where the center of that circle that is currently washing over him is. He's stationary. That circle is just expanding outward at the same speed in all directions. No question, he sees that circle expanding at the speed of light because he is in the ether. He's stationary in the ether. So he sees it moving at the speed of light. And it's moving out radially. So if he looks back to where that light was coming from, he looks back to where the source was when it emitted that light. So that's that green arrow from 1 is pointing to where the source was when it emitted the light that he's now seeing. And I can say all of that for each of the other observers as well. Same thing. Notice that observer 2 is the light has gotten to observer 2 relatively quickly. He's not very far away from the place where the light was emitted when it got to him. The circle that's washing over him is a smaller circle. So it wasn't as long ago that the source was where he sees the light coming from. And then observer 3 is a little further away. He's seeing a slightly larger circle wash over him right now, but all the same things. Notice that those green arrows point to all sorts of different locations. They point to the center of the circle that's currently washing over each one of those observers. And that doesn't, and there should be a lot of things that kind of are puzzling about that, right? Observer one, the source is almost to observer one. So why isn't he seeing it closer to where it really is? Well, the problem is, of course, he can only see the light that is currently getting to him. And the light that is currently getting to him came some time ago, right? In fact, observer one is seeing light from the longest ago. He's on the outermost circle. Observer four is on, maybe the second most outermost circle. So where he sees the light was not from as long ago. For to him, there's a lot of very puzzling things going on in this diagram, if you think of it as I kind of describe in bullet point one there. But now let's think about bullet point two, because these observers also represent what observer one will be seeing at equally spaced later intervals of time. Because if I wait a little bit longer, this whole pattern will be repeated to the right. All of the circles will have gotten larger, but each one will have been replaced by a new one, and the entire pattern, as it looks there, will simply be moved to the right by a distance equal to the distance between lambda 1 and, or lambda, why do I keep saying that? Observer 1 and observer 2. So observer 2 really just represents what observer 1 will be seeing in a bit. And observer 3 just represents what observer 1 will be seeing twice as long in the future. And observer 4 just represents what observer 1 will be seeing 3 times as long in the future. Okay. Comments, questions about that? It's a little tricky to think about, but I really want to exploit that. Observer 1, 2, 3, 4 just all represent observer 1 at a later, a double later, and a triple later moment of time. So let's just take those green arrows and gather them together as is shown in slide 11. If I just take the single observer and I take those 4 green arrows and attach them now to that observer sees the source originally at position 1, and then sees it at position 2, and then sees it at position 3, and then sees it at position 4. And that should make sense, right? He's seeing the source move past him to the right, above and past him to the right. So that should all just kind of make sense. But, and this is kind of the extra credit thing here, I'm just going to say this. If anybody wants to pipe up now, that's fine. We can talk about it later if we want. Notice, because I've tried to draw this really carefully, and so I want you to notice that even though 1, 2, 3, and 4 represent equal intervals of time, he sees the sun move much further between 1 and 2 than he does between 3 and 4. And yet that source is moving at a constant speed. So how is it that he sees the source? These are equal intervals of time as he sees it, but he sees the object move further between instance 1 and 2 than it does between instance 3 and 4. So what's going on there? And you don't have to answer that question, but if anybody wants to, just unmute and let me know. And I won't wait long.
We've
Go
seen
ahead,
this
Shamash.
before. We've seen this
Yeah.
before when we did the twin paradox episode.
Yes.
So as
This
these wave hits, depending on your position, as the object is moving closer towards you or far away from you, you would receive signals at different intervals. And so if you have a constant speed in your equation, you will interpret that as bigger distances.
Well, okay, so I'm not sure that.
Wait, are we still talking about light waves or?
Yeah, we are
Not.
talking about light waves. We're talking about what the observer sees. We have determined what the observer will see in terms of those directions, which have to be perpendicular to the wavefront that is at each instant passing over the observer. Each of those green arrows is perpendicular inward toward the center of the wavefront circle that's currently passing by that of each observer. So really, this is a really complex thing. You probably have to spend some time kind of thinking about it.
Well, for the full answer, you would need relativity, but
Nope, no, you do not need relativity. We are not in relativity. These are waves in a medium. These are not,
then
these are
that's why
not
then it's not
electromagnetic
light
waves.
Then it's
Yeah.
not light waves.
They are light waves, right? They're light waves as they were understood in the early 1800s.
Oh, okay, I see.
Yeah. They're wrong. You're right that their
Yeah, of course they're
understanding was wrong, but we don't know that yet because we're not there. Okay,
Gotcha,
but
gotcha.
nevertheless, this is something that would happen and does happen with real objects, sources moving through media, objects that emit waves. Shamash is on to it, but I'm not sure I find your explanation compelling. Let's come back to this maybe in 5 more slides to do, and then we'll be done. Okay, but that's a nice little extra credit problem for you. Let's move on to slide 12. What does a moving observer see in the case that we're talking about? Now, this gets really complicated, so I want to simplify it enormously by talking only about an observer that moves with the source. Both the observer and the source are moving in the same direction at the same velocity through the ether. Both of them, same velocity, same direction. They're just offset. So the observer, the green, the blue guy here, is moving to the right. The source is also moving to the right, and the source is always directly above the head of the observer. Okay. But I want to also look at things from the reference frame of the observer and the source. So I'm looking at this now in a reference frame where it's the ether that's moving. The ether is moving to the left. So it's like me standing in a river, right, with a source over just a little, somebody dipping his finger to the side of me, and the river is flowing past. The guy dipping his finger is making these waves. The waves are traveling out from there, but they're being carried downstream by the river. There's an ether wind to the left. So what does the observer see? And I'm just going to tell you this. You can decide whether it makes sense. It's right. And by the way, I had the wrong, when I first did this, I had the wrong diagram. This morning I woke up in horror because I had actually given you an explanation here that was wrong. Now I'm telling you the right thing, so that's no longer operative. But here's what happens is the observer is right there, and that wave front, if in general you'd think, well, the light is traveling perpendicular to the wavefront, so he would have to look back toward the perpendicular to that, to the center of that circle to find the source. But the problem is that wavefront is not really expanding out that way. It's being carried downstream as well by the ether wind. So you have to do the little vector addition that I show at the bottom there. You've got to add to the motion of the wavefront in the ether, you have to add the motion of the ether to the observer to get what the observer sees as the apparent direction of the light. So the observer is actually going to see the light coming from the direction opposite that green arrow. And if you notice, that means that the observer will literally see the light coming from the place that it was emitted in his reference frame. It came from that light source. That light source in this reference frame has always been there. The observer has always been there. It's the ether that's moving to the left, not the source, not the observer. And the observer sees the light coming from that source, just as he should. Even though the actual source of that wavefront was over there to the left, as I've shown. The actual source of that wavefront is over to the left. That's where it came from in the ether, but that's not where he sees it coming from. He sees it coming apparently from the place where where the source is now and always has been. There's a lot of weird stuff going on there too. So as I say, despite the fact that the light being observed now actually came from the point shown, the center of that wavefront, the observer sees the light coming from the place where the source always has been in his reference frame, directly above him. So that's kind of
Hold up.
that's an
Does
interesting
that
little
imply that
conundrum.
that the sun doesn't move in that way? Because if he's moving with the wave front and he's always seeing it coming from the center of the wave, how would he know that it's moving?
Yeah, no, that's right. I haven't. That's a really good point, and I should have emphasized. He doesn't, right? All he
My
knows is what he
God.
sees.
Okay. Oh my God. All right.
That's right. No, he doesn't know any of this. I'm just telling you that if we want to actually talk about what's really going on, kind of from a God's eye view, we can see that this is what's really going on. All he knows, if he doesn't feel the ether wind, and he doesn't, none of us do, we don't know yet that that's because it doesn't exist. Is all he knows is that he sees the light, and he doesn't know that he's seeing the light or the source. He doesn't even know that, right? He doesn't even know for sure that he's seeing the light coming from where the source really is, but we do. So that's all I'm really saying.
Does his speed affect this? Like, would if he was very, very slow, would he see the source
Yeah.
traveling slow? Yeah.
Well, so this is what I really don't want to get into quite yet.
Yeah.
To
Okay.
do
Okay.
anything but this really simple example, it just makes the math, the vector addition, even more complicated than it already is. And I think this is about
Yeah.
one of the
But
most
in your
complicated
example,
things I've ever done.
in your example, he's moving at the same speed as the source, right? With the
Right.
wave. Yeah. Yeah. Okay.
Right. Now, I believe, I'm pretty sure that we can show, it would be difficult, but we could actually show that, in fact, we no matter what his actual motion is, he will see the light coming from where the source really was when it emitted that light, just like in the particle theory. Right. And so, getting ahead of myself a little bit, but what we're going to see is that whether light is a particle or a wave, we can calculate things like aberration either by assuming that there's a rain coming from some direction, and then adding my velocity to that to figure out what I'm going to see, or by assuming that the light simply comes straight to me in my reference frame from the source. Either of those will give the right answer, no matter whether light is a particle or a wave. But it makes more sense to do one of them if light's a particle, and it makes more sense to do the other one if light's a wave. It's just technically more correct. So that's kind of an interesting little thing, and I want to carry that forward to when we talk about relativity. So I did get a little ahead of myself there. So let's move on to slide 13, where I show how we actually do this calculation for aberration. And I'm doing it now in this kind of rain idea. Imagine that I just simply look at two observers. I've got a blue guy seeing light coming. The rain of light just means that this light is coming from a long ways away. This is probably the best way to think about it. If the light is coming from a long ways away, then the wave front passing over the blue guy is basically a straight line. It's an arc of a circle with an enormously large radius. So it's just a straight line perpendicular to all of those rays that I'm showing. And so it really does, it's nice to think of it as just blue rain coming from some direction. That's going to be the direction that he sees the light source in. And then there's a red guy who's moving to the right relative to the blue guy. So I've shown what it looks like from the blue guy's reference frame. And right down below, I'm showing what it looks like from the red guy's reference frame. The red guy, if the red guy is the stationary one, then he's going to see the blue guy moving to the left. And because of his relative motion, he's going to see the light coming down at a sharper angle than the blue guy did. And it's important, it is a sharper angle, not a steeper angle, but a shallower angle. I guess I should have said not sharper. It's coming down at a shallower angle, not a steeper angle. And I've shown then the two angles that I'm going to refer to. Theta r is the angle that the red light makes with the direction of motion, and theta blue is the angle that the light makes with respect to that same direction, the direction of relative motion, I should say, for the blue guy and for the red guy. Those are the two angles. So I'm just going to tell you, this is really not at all hard to derive if you know a little trigonometry and a little vector addition, but it's not hard to show that if Mr. Blue is at rest with respect to the ether, if the blue frame is the ether frame, then the angle that the red guy sees is the arctangent of the sine of the angle that the blue guy sees, which is the preferred, that's the real one, right? That's because blue is now the preferred observer, divided by the cosine of his angle, plus the ratio of the relative velocity of red to blue, divided by the speed of light. So pretty simple formula to calculate. The red guy who is not in the ether, right? It's the blue guy that's in the ether, then the red guy will see that angle. But if it's the red guy, if Ms. Red, the red guy, the red gal, if Ms. Red is the one who's at rest with respect to the ether, then we can calculate the angle that the blue guy will see. And you see it's almost exactly the same. The only difference is that I subtract V over C in the denominator rather than adding it. But my point is to say that it does make a difference. The angle that you'll calculate will be different. Those two angles will be related differently if blue is at rest in the ether than if red is at rest in the ether. So you might think, there's a way to tell. Well, it's not really a way to tell because you have to kind of know which one is right somehow. But let's see what the net result of this is in the next slide. Let me just stop for a second. Let me stop at least to say hi to Ben. Thanks, Ben, for showing up. Good to see you. And
thanks, John. Yep. Cool. Good to see you. I think there's a typo on a couple of slides in the future, but I'll see if I can comment before you get there.
Okay. A couple slides back.
No, forward. But it's right. If I can get the comment access, so I might even have edit access. I can just fix it. So anyway, cool.
Okay.
Enjoy. I'm enjoying. Sorry, I'm so late as usual, but
family time. I know.
Just can't get the staff these days.
Ben's across the pond. It's a bad time for him. Okay, so let's look at the results then. On slide 14, I repeat the formulas. And I just give you a couple of examples. Suppose that it's blue that's at rest, and he sees an angle of 70 degrees. And let's suppose that the red observer is moving at 1/10 of the speed of light. That's really fast. As you can see, moving fast to the right means that the Ms. Red will see the light coming down at a shallower angle, kind of has to point her umbrella in the direction that she's moving. And what's the angle that she sees? Well, we can calculate that using the formula I gave, and we see that red will see an angle of 64.81 degrees. That's a difference of 5.19 degrees between the blue and the red observer. And that would be an aberration angle. This is aberration. This is a difference in apparent position of a star, direction to a star, by virtue of moving through the rain of light coming from that star. This is an enormous aberration. If stars did that kind of thing, moved around by 5 degrees one way, 5 degrees another way, we would notice this. Right? It would be something that we would notice pretty easily. But we don't, because things don't move that fast in general. But let's just do the alternate calculation. Suppose it's red that's at rest, and suppose that red does see an angle of 64.81 degrees. But now it's red that's at rest, and blue is the one that's moving at 1/10 the speed of light. Then we have to use the other formula, and what we get when we use that other formula is that blue will see an angle of 70.21 degrees for an aberration angle of 5.4 degrees. That's a 4% difference in the aberration angle if red is the one that's at rest, to the case where blue is at rest. So it makes a difference. That's the point I wanted to make here. The formula gives different results depending on which one is at rest with respect to the ether. But what I want to point out in the next slide, the penultimate slide, is that if you go to more reasonable values for velocity, it doesn't make a difference. I shouldn't say it doesn't make a difference. It doesn't make a detectable difference. So here I'm going to do the same thing again, but I'm going to use more typical values for speeds relative to the speed of light. And I'll remind you, I'm not talking about relativity yet. This V over C, this is purely classical. There's no relativity in this. But people in the 1800s knew that the speed of light was about 186,000 miles per second. They had pretty good values. They knew it was about 180 to 190, I should say, 1,000 miles per second. They knew it was fast. They knew pretty much what its value was. And they also knew that the Earth moves about 10,000 times slower around the sun than light does. And that nearby stars, they were starting to even understand that nearby stars moved at speeds like that. More typical speeds for things near Earth, including Earth itself, relative to other things around us, are 10 to 100 kilometers per second. Those are the kinds of speeds that stars move at relative to other stars, that planets move at around stars, etc. So let's take that then and use as a number a V over C of 1/10,000th. Start with the same angle. Suppose the angle that blue sees is 70 degrees, but now let V over C be 1/10,000th, 0.0001. We use the same formula again, and now we calculate that the red observer will see 69.999461614 degrees. That's an aberration angle, a difference between
Hold
the
on,
70.
Objection, Your Honor. Too many significant figures.
It's actually not. Surprisingly enough, it actually isn't, because I can work this. I can work this formula to get a direct formula for the difference. And if I can measure the so let me get back to that in just a second. This actually is not a case, though, it is a case of too many, but not as many more as you might think, significant figures. If I just take those two numbers and I subtract them, I get 0.0053839 degrees of aberration. That turns out to be about 1920 arc seconds. There, now I'm getting back to a correct number of significant figures. And we can measure the aberration angle pretty accurately. Bradley measured the aberration angle to 3 significant figures. He had some uncertainty in the third one, but he measured an aberration angle of about 20 arc seconds, just like this. So that aberration angle we get is 19.4 arc seconds. In this case, if I made the alternate calculation, suppose that red is at rest, and let's just suppose that that she sees that angle that we just calculated? What if she sees that angle that we just calculated and it's blue that's moving at 1/10,000th the speed of light? Then we have to use the other formula, and when we do, we get that B sees an angle of 70.0000018 degrees. So once again, it does make a difference, but now Ben is absolutely right to point out that I have carried too many significant figures in the sense that there is no way to observe that little difference. The aberration angle in this case, rather than being 0.005839 degrees, is now 0.0053840 degrees, which rounds off to exactly the same observable aberration angle of 19.4 arc seconds. So to within our ability to measure these things, it makes no difference whatsoever in practice. If things moved much faster, we would notice these things, but things do not move much faster. And so we've never seen this make a difference. And so I just end here with the fact that in practice, it doesn't even matter if either of them are at rest. The only thing that matters is that the speeds that we're talking about are small compared to c. I'm going to get an aberration angle of 19.4 arc seconds in this case, regardless of what the actual velocity of the ether is, as long as it's not a significant fraction of the speed of light. It doesn't matter. I can't detect the motion of the ether this way. All I can do is get the aberration angle that depends only on the relative velocities between the two objects. Okay, so that's kind of really the end of the presentation today. I do want to look forward, but let me just stop for a moment, see if there are any questions on that, and then we'll open it up for discussion. Hearing nobody jump on it, let me just look forward a little bit, and then I will formally finish, and we can talk about whatever you want, including the extra credit assignment, maybe. So looking forward, what I've tried to show you today is that in both the particle and the wave views, one can calculate the apparent direction of a light source. Jump on it. Let me just look forward a little bit, and then I will light comes directly from the light source to each observer in their own rest frame, or from the assumption that there is a real pre-existing rain of light through which observers may or may not move. You can calculate the aberration either way. In both views, both methods work. Either method gives the right answer in both cases, but method one is technically only appropriate for the particle view, and method two is technically appropriate only for the wave view. Oh, there I see a typo. So in the final two parts of this series, we will first look at attempts to observe real effects of the ether in experiments done by Arago, who looked for its effects on refraction, Fizeau, who looked for its effects on light speed in moving water, and Airy, who looked for its effects on stellar aberration using telescopes filled with water. He actually filled telescopes with water and maybe mineral oil, I'm not sure, and tried to see if the aberration changed when he changed the speed of light in the telescope itself. Then we'll see how Fresnel managed to sweep all of their failures. All of those attempts to see the effects failed. And I shouldn't really say that. I guess that's not the right way to say it. But Fresnel did manage to sweep the failures to detect the ether under the rug with a really clever hypothesis of what's called the partial ether drag hypothesis. That hypothesis turns out, Fresnel didn't know it at the time, but he was really deriving what turns out to be the relativistic velocity addition formula, but he didn't think about it that way at all. He thought he was sweeping away the failure to observe the ether with this hypothesis that kind of explained why they weren't able to detect it. And then we'll see how Michelson and Morley in the end of the 1800s actually showed that even Fresnel's hypothesis wasn't powerful enough to prevent the final conclusion that if the ether exists at all, there's no way to detect it. And it wasn't long after that that scientists, this is where Shamash comes in with his philosophy of science, you're now putting into a scientific theory an element for which there is no evidence and can never be any evidence. Einstein looked at that and basically put his philosopher hat on and said, if there can be no evidence, if there can be no effects observed of the ether, then I'm just going to say it doesn't exist. And accept the fact shown by Michelson and Morley that the speed of light is just the same for all observers, regardless of how fast they're moving. It doesn't change. And then we'll see how the special theory of relativity arose as, and effectively, I don't want to say completely necessary because Shamash would object, but it looked like an effectively necessary consequence of the fact that there was no way to observe the ether. And then we'll be done. I don't know if I think I'm probably going to do this in 2 more installments, but that's where we're going. And we've already talked about relativity in several bites of physics, so I'm not going to go further in this particular episode. But if you're interested, you can look up in my catalog of bites of physics, to which there's a link on the first slide. And I'm done. So any comments or questions or anything else? Happy to entertain at this point.
Okay, since nobody wants to do anything, can we go back to that extra assignment?
Okay.
Okay,
Which
so
slide was that?
I don't know.
Let's see. That was on slide. Oh, where was it? There it is. 11. Slide 11.
Okay, so my thought process was the following. Since there is no Doppler, there's no relativity, there's none of that stuff. The observer's clock now, assuming that the source is moving at a constant speed and it's a wave, so it must be moving at a uniform speed as a wave. The observer's clock is only the waves they are receiving. So as the source is moving towards them, they will receive click, 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 click in succession. And that would mean 1 meter, 2 meters, 3 meters, 4 meters. Whereas as the source is moving away from them, the clicks will be further apart. And the only explanation for that is, if we want to disregard the fact that you might see the actual waves being modified, the only way you can make a constant speed with that is if you change the distances as well. So the times are becoming shorter and bigger. What is the consequence? To keep a constant velocity, you have to make the distances go also bigger and shorter, inversely proportional.
Yeah.
So according to your calculations, you will get bigger distances. That's the only explanation between 1 and 2.
I think that's right. And let me try to, I think, clean it up a little bit just by saying that between seeing 1 and 2, the observer, these are equal times, right? I mean, he sees the source at position 1 at some time. He sees it at position 2, let's say 10 seconds later. And then he sees it at position 3, 20 seconds later. And then he sees it at position 4, 30 seconds later. It's his time that's the same between each one of those. But I think the thing I really like about your way, I hadn't thought about it this way, is that between 1 and 2, he's seeing wave fronts come by him, click, 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 click. And between 3 and 4, he's seeing wave fronts come by him, click, click, click. Right? So more wave fronts came by him between 1 and 2 than did between 3 and 4, and that corresponds to the source having moved further between 1 and 2 than between 3 and 4. Does that sound like a different way of saying the same thing?
Although the actual source from a God point of view hasn't.
Well, I don't know that I'd even say that. It's not that it hasn't. You just have to really recognize what it means when he sees it. And this is why I think maybe it's a better way to think about it has to do with if you go back to Bitophysics number one, you might want to review Bitophysics number
Whoa,
one.
this is way before I was a thing.
That's right. In Bitophysics number one, we talked about what it would look like if you were standing on the moon and somebody shone a laser beam from Earth, swiped it across the moon so that the spot on the moon moves faster than the speed of light. That's something that you can do because all you have to do is just turn the laser fast enough such that the angular velocity of the laser times the distance to the moon is greater than the speed of light. And you can do that easily. It's really easy to do that. It doesn't require a very fast flick. The spot of light will move at an arbitrarily large velocity. And then you ask, what do you see standing on the moon? And the answer we came to was the first thing you see is a flash of light as the laser passes over your head. You see, bam, flash of light right at your feet. There's a spot of light right at your feet. And then as time goes on, that spot of light races off quickly in the direction that it came from because it takes longer for the light from those spots to get to you than it did for the spot itself to get to you. So you see the spots in successive times racing away from you in the direction that the spot came from. And you also see the spot moving away from you in the direction that it's actually going, but slower. And it has to do with the fact that it takes time for light to get to you from something, whether it's moving toward you or away from you. So the way to think about this one is that the light that's coming from the source when it's at position 1 takes a long time to get to you. Meanwhile, the source has moved closer and it's emitted other light, and you're going to get that light in much less time. So the time between arrivals of those two light sources is much less than the actual time between the emissions of those two lights. If a spaceship comes toward you at 9/10 the speed of light, you will see it really far away, and then it will come toward you apparently at like 3 or 4 times the speed of light because you see it a long ways away. It was now moving toward you, following in close succession behind the light that it already emitted toward you. And then, at your end, you see all that light and the spaceship itself get to you in a very short amount of time. So it looks like the spaceship's traveling much faster than it really is. Whereas the exact opposite happens when it moves in the other direction. That maybe takes more pictures and things.
So I had a thought on that. Are we looking at slide 11?
Yeah.
Okay. So if you have these apparent positions of the light source, 1, 2, 3, 4. If you had started that further to the left, if you had a position 0,
Okay.
like,
Or a
okay,
position -7 or something.
yeah. If you had like 10 of them and they really went further to the left and further to the right, the way you drew it kind of makes it. It seems like you're suggesting the further to the left you go, the wider the angle. But I think if you went far enough to the left, the angle would start getting smaller, just like 3 and 4 is smaller, and they would get smaller off to the left. But they get closer, the angles get bigger, and then I guess what you're saying is the biggest angle is sort of skewed to the left, not. But in any case, they get smaller as they get to the left and the right.
Well,
Correct?
so let me. I like.
Does that,
I mean,
does
it
that
is
make
really
sense?
important to think about you're really onto something by adding -10, -9, -8, etc., negative infinity if you want, and by adding 7, 8, 9, 10, positive infinity, because really, if you do that, then what you're going to actually see is that for the vast majority of the time, the source was coming almost directly at you or directly away from you. There was only a short period of time when it was kind of what you might call passing you, right? And during all of the time when it was coming toward you, it's going to appear to be moving fast, pretty much the same speed. All of those angles will be very much, to the left. Whereas after it's passed you, long after it's passed you, all of those angles are going to be very much to the right, and it is basically just moving away from you. When it moves away from you, it's going to look like it's moving really slowly, because every successive distance that it goes, the light takes longer to get to you. So you don't see it get to that next position until even longer than when it was at the previous position. Just the opposite happens on the way in. So basically, it is, Shamash had said something about there being no Doppler effect, but there is. I mean, there's definitely a Doppler effect.
Oh yeah,
This is
absolutely. You
classic.
would
Yeah,
detect it, definitely.
yeah. This is classic Doppler effect. And that Doppler effect manifests in terms of visual things, just in terms of the object itself looking like it's traveling faster than it is when it comes toward you, and looking like it's traveling slower than it is when it's moving away from you. And so the bad part about my drawing there is that it only shows that weird, kind of harder to sort out region where it's passing you.
Yeah, but the others are easy to guess. Like you can imagine, the limit easily. It's this horizontal vectors that you have. This is exactly what you will see.
So did that all make sense, Andy? I think I was saying pretty much what you were saying.
Yeah, I think so.
Yeah.
It's all good. I have another question though. This might be silly. On your equations on 13, 14, and 15, so I was thinking about it, that you chose to have two different equations, and I was thinking like, well, gee, how does blue and red know which equation to use? There's two
Yeah.
equations, and I thought, well, I think you're trying to demonstrate. So, like, I was thinking that it should just be one equation, and the negative sign should be in your v. Like, if you're going the red direction, it's negative, and if you're going the blue direction, and I thought maybe what you were getting at is like, well, why should they have to agree on a direction in order to make this work? But then again, they would have to agree on which equation to use. So I'm just curious why you chose to put the plus or minus in the equation and not in the velocity.
Right. No, that's good. And so I think this is related to the fact I didn't talk about one thing on slide 15 right at the end that I will now in as I answer your question. What I was trying to really make the point here is that, see, it's unlikely that either blue or red are at rest with respect to the ether, right? It's probably the case that neither of them is. And what I really should be writing there is that the angle that either of them see depends on the actual angle. And by actual angle, I mean the angle in the rest frame of the ether, whatever that is. That should be the thing that I'm taking the sine and cosine of in the thing. And then, yes, and then it should just be a plus or minus v with respect to that frame. But to make things a little simpler, I wanted to just say, well, let's just suppose, for the sake of argument, that B is the ether frame, and then let's suppose that R is the ether frame. And I wanted to do the two equations so that I could quickly calculate those kind of, take the 70-degree angle for blue, find the corresponding angle for red if blue was at rest, and then take that same angle for red and say, well, what if red was actually at rest and that was the angle that red saw? Do we get the blue angle back? Well, we don't, because it does make a difference which one is in the ether frame, and it does in general. But then what I did on slide 15 was just to point out that in practice, we never make these observations moving with respect to anything at a speed that's large enough to actually be able to tell the difference between those two. And indeed, we can't even know for sure. It doesn't in the end matter at all whether either one is moving, is at rest in the ether, or even what the ether is doing. The fact of the matter is that as long as the speeds are small compared to any velocities relative to the ether, compared to any sources or anything else moving relative to the ether, the actual formula for all practical purposes is simply V over C times the sine of the angle that you see. And when I say you, I mean, I don't care if you're the red person or the blue, just take the sine of whatever that angle is, multiply it by the relative speed of the other observer divided by C. And that is the aberration angle. Nobody has ever observed an aberration angle that differs from that simple calculation. The actual formula for all practical purposes is just V over C times sine theta.
That's kind of hence my glib comment about significant figures.
Yeah, right. And if you do that, I should have done that in this case. I mean, if you just take V over C times sine theta and put in either 70 degrees or 69.99464 degrees or 70.000018 degrees, you put in any of those angles, you'll get 19.4 seconds. And nobody's ever been able to make a measurement. I shouldn't say that. I guess it's conceivable at this point that we might actually be able to make measurements that are so accurate that we would actually tell the difference. But I don't think so. I think nobody's ever made a measurement where it makes a difference. You can just use the V over C sine theta calculation.
I thought I understood, and now that you've explained it, I think I haven't. So just bear with me here, if you may. The picture on the top that has blue rain, this is the blue person's perspective, right?
Right.
And the picture on the bottom is the red person's perspective.
Right.
And they are both looking at the same source. It's just that in the first picture, what we're describing is someone who is stationary to the ether, looking at a moving source of light.
Well, notice that in the pictures I didn't specify which one. I just drew the two pictures, and then I said if the blue one is the one that's at rest.
Okay.
Yeah. Okay.
So my question is, the only reason the blue person is seeing the light, the rain bent and not perfectly vertical, is because the source is moving.
No, I wouldn't say that. I wanted mostly to make it not be straight down so that I didn't make anybody think that that was important. Doesn't matter what angle it comes at. The only thing that matters is the angle that the direction to the source is, the direction it appears to be, that the angle that it makes with the relative velocity. That's the only thing. And so I probably should have made the relative velocity be in some other direction other than horizontal too, because that's what in the bottom diagram there, the only reason I have that horizontal line to measure the angles is because that's the direction of the relative velocity.
Yeah, so the relative velocity, meaning the movement between the two people, not the movement of the source itself. Yeah, okay. And then the reason is the reason that red perceives the angle to be sharper is what exactly?
So you can, from either point of view, look at it from the blue frame. If I look at it from the blue frame, the red person is moving to the right, right? So if that really were rain, I think this is the easiest way to think about it. It's just a vector addition thing. But if that really were rain, then the red person would need to tilt her umbrella to the right, to shield herself from it, because she'd be running into the rain. It appears to come down at a shallower angle, as I show with the direction of the red light.
Okay. I get it. Okay.
Yeah.
Okay.
Right.
So
and you can do the same thing from the other.
Yeah.
Right. The blue, if you look at it in the red frame, the blue person sees that rain, but because he's moving, you know, moving to the moving in the direction that he's moving, he's going to have to actually tilt his umbrella upward. That's maybe not quite as obvious, right? But if you move with the rain, there comes a point where if you move fast enough, that rain is coming straight down.
Straight down, yeah, you make it vertical, exactly. So
Right.
if one of them moves very, very quickly, the equations will be reversed. And this is what you will have here with the sines and the cosines. They do that game.
Right.
Yeah, okay, that's wonderful.
Yeah, and so ultimately, as I say, the only thing that really matters now remember that in at the time frame that we're talking about, we knew what the speed of light was, but people still thought that if you move toward a source, the light should be faster, and if you moved away from it, it should be slower, right? It worked like Doppler effect, or like waves in any medium do. So there would be. I have just noticed. I've just kind of blithely put the speed of light in these equations, but even in the 1800s with the wave theory, the speed of light wasn't a number. They just knew that it was so fast that the velocities that normal things move isn't going to make a very noticeable difference in the speed of light. They did. I mean, a lot of the experiments being done in the 1800s were, some of them were attempts to actually detect the differences in the speed of light. What Arago was doing was trying to find differences in the speed of light by looking. He actually looked at starlight through telescopes. I assume he must have focused this light down, and then he passed it through prisms, and he thought that he might see starlight bent differently by the prism in June than it is in December, because we were either moving toward the star or away from the star, and the speed of light would change, and the amount of refraction depends on the speed of light, so it would change. And he didn't see anything. That was the first of the failures to see. And it was due to Arago. I don't know how you pronounce that name. Somebody can correct me on that. It was due to him. He apparently asked Fresnel why if Fresnel could come up with a reason that he wasn't seeing any difference. And Fresnel developed, as I understand it, his partial ether drag theory in order to explain why Arago didn't see any effect of the ether in his measurements. We'll talk about that more next
Yeah,
week.
this all in my head goes back to that question, that very clever question you asked in the last episode, which is, why haven't we measured the speed of light to be 1 miles per second?
Right.
So because the
Well,
reason is because you can't.
and when the interesting thing is that one of the results of them asking that question was that one of the things that appears to be, as I understand it from my conversations with Gemini and others, a lot of people thought that that light did travel at any speed, that those particles could travel at any speed, but that the eye was only sensitive to them when they traveled in a very narrow range of speeds.
Oh,
And remember, Newton kind of got some evidence for that, because he showed that there were effects when he spread white light in a prism. On the red side of the spectrum, he could heat things up even though he couldn't see any light there. And on the blue side, he could make chemical reactions happen even though he couldn't see anything there. So that was kind of a compelling idea.
and then the explanation was, hold up a second. Doesn't that lead immediately to them understanding that as light goes through the prism, it changes speeds? Isn't it like a direct consequence?
Well,
But they
that was
didn't know
a
that at the time.
large part of the. I mean, people didn't really know exactly why refraction happened, but it was very convenient. An obvious thing was to say that refraction was a result of the fact that different different colors travel at different speeds, right? What makes blue light is that it's particles traveling at blue speed, and etc.
Yeah, and so then the bigger than blue and the smaller than red are just too slow for us to see, and too big for us to see, too fast.
Right. The interesting thing is that a prism, I mean, those of us infected with an understanding of 20th century physics would probably think that blue light ought to be refracted less than red light because blue light corresponds to photons of high energy. And you know, if you just kind of think about that, you say, oh, high energy photons, they're gonna not be bent very much by a prism. But it turns out it's just the other way around. Because it doesn't have anything to do with the energy. It's something else that makes light refract.
The major error here is, I think, who was it? Was it Fraunhofer? No, it wasn't. I forgot who it was. When they discovered when they put the thermometers on the table, and then it was the discovery of infrared and ultraviolet.
Right. Well, that's what, of course, Newton did. Newton actually did discover infrared and ultraviolet. He just didn't call them that.
Yeah, but he didn't do the experiment where he measured the temperatures of the colors. It was someone else.
Oh, I don't know. I'm not sure what you're referring to there.
I'll Google. I don't know. I'll Google the name. But the experiment is, he wanted to see whether these rays of light had different energies. And of course, what does a light with a bigger energy do? It's light that makes things hotter. And so he put a prism like Newton did 100 years ago, and he had 7 thermometers on the table, one for each color. And then on the far left, he had his 8th thermometer, like on the left of red, just as a control to see the temperature in the room. And then it turns out that the one that doesn't have light on it had the hottest temperature. And everybody assumed that infrared light had bigger energy since then, because the infrared one had the highest temperature in that experiment, whereas it turns out that the spread caused by the prism made the bluer light less concentrated, and so it caused the thermometer not to give that higher number. But we know now that the bluer light has higher energy.
You know, if different color light really traveled different speeds, things that are far away would be all messed up. Like,
yeah,
why would they look white to begin with?
They would be all blurry and weird, and
yeah, that's right. I mean, I think, well, so I don't know. Right, it's not so much, of course, that they wouldn't, but you would expect to see the slower light kind of on the trailing edge, right? If a star were moving to the right, then you'd see kind of the slower light on the trailing edge of that star, et cetera. And I think this is the kind of thing, it was that kind of thing that Arago was looking for the effects of speed. He was looking more just in terms of toward us or away from us effects on the speed. I haven't, it occurred to me too that what you're saying, Andy, I don't really know specifically of whether he did experiments to look and see if stars had kind of a red side and a blue side to them, which you might expect. I haven't heard anybody say that he did that, but it's kind of hard for me to imagine that he wouldn't have.
Well,
wait a second.
To maintain
I'm
that
so
belief,
dumb.
you'd have to think that things are relatively close to us and that everything was kind of staying still.
Right, but I think I think by this point we knew that the stars were really far away because Bradley had failed to detect parallax in any of them. So he knew that the parallax was much less than 20 arc seconds. Turns out the highest parallax star, the nearest star to us, shows a parallax of less than 1 arc second. And you have to look all through the sky to find that one, right? Most of them are like 1/10 of an arc second or 100th of an arc second. And we knew what that meant, right? Because that's just simply the size of the orbit times that angle, or divided by that angle, gives you enormous distances.
This might be a little off topic, if you don't mind me asking.
Sure, go ahead.
Do you have any thoughts on like string theory, like the foundations and influence or motivations for what string theory is useful for, and where the prospects of string theory necessarily?
I knew Benjamin would come off mute for that one. Go ahead, Benjamin. I'm going to toss this one to you.
Nobody here has any ideas about string theory, or anywhere.
Yeah, this is if you really should have some conversations with Benjamin. It's an area. Benjamin has some takes on this that are a little firmer than my take, but not particularly different. String theory has largely failed. People are still looking. There may be elements of it that are useful in some future theory. But I think it is looked on, at least right now, as only a vehicle for destroying the career of a generation of physicists.
Success.
Success.
Before they embarked on this, did they not know that the energy is required to get the observations to tell how useful to sort the theories out were going to be beyond reach? I mean,
That's a good question. I don't know for sure that they knew that. I mean, they might have imagined, and I think you could still imagine that you could come up with some kind of a string-like theory that would have some implications that might be detectable, at moderate energies. There are things like, for instance, I mean, the fact that there are 3 families of quarks and 3 families of leptons is very interesting, right? Why 3 families of each one? And I don't know what the current thinking is, but I know that there are implications of that go well beyond just thinking about the standard model. I should Google that. Anybody who wants to, if you want a fun conversation with Gemini, ask Gemini, as I probably will later on today, why any ideas about why there are 3 families? And I guarantee you there'll be answers, because people have been talking about that for at least 20, 30 years. And I know that there are some pretty firm ideas about what that means, that there's a reason that there are 3. And that reason makes a lot of sense. But I can't remember what it is.
Yeah, I think that remains a mystery. But the one part of Jesse's question had a really easy answer. The question of the usefulness, and there is no utility in string theory. And I think even if it was successful, there still might not be any utility in it.
Yeah.
Yeah. The way I always look at this,
now.
Oh, go on. Go, ladies first, Benjamin. You've got a longer version of my name. So.
My name is bigger than yours. The children of string theorists who have eaten well for a generation off the taxpayers would beg to differ with your claim.
Oh, I thought you were
utility in string theory.
Oh, I thought you were going to point to the fact that most of them have gone on to be very successful in stock market.
Well, they are the children who ate all this tax dollars are very healthy, very happy, very well fed.
The techniques, the mathematical techniques that they learn in string theory,
the techniques of transferring tax dollars to your pocket through the use of string theory has been very successful. It's been demonstrated over and over again. It's highly utilitarian.
So, I don't know.
Yeah, go ahead, Ben, and then we'll go to CM.
I got 2 comments here, I guess. No plan survives contact with the enemy, sort of thing. So you go into this thinking you're going to progress physics. The act of trying to solve it is going to have left mathematical frameworks and useful traces behind whatever happens to the string theory, whether it turns out to be useful in the future or not, that will be picked up by future generations. I'm firstly confident in that. And secondly, I'm also want to make the observation that I think that it's the same thing to say whether something's useful and whether it's validatable. The moment you can build the technology to measure whether a theory is more precise than the previous one, that's kind of the same thing as then making use of the technology. Maybe the making use of the technology comes a little bit later. but it's all just super premature because of the energies involved. That's kind of how I see it. But
Hmm. Go ahead,
Yeah,
Sam.
but I mean,
Oh, hold on,
with
Ben.
Hey
this
guys.
argument, right? Go ahead.
Well, okay.
So
Yeah,
we're
quick
we're talking
response to
about
Ben. Quick response to Ben, and then we'll go to CM.
Quick response to Ben, which is this claim that, well, anything, if you study it well enough and hard enough, creates advantages for the future. I think, I owe an apology to the Franciscan monks for studying the way in which a wafer, when you pray over it, is converted into the body and the blood of Christ. It may not happen in science, but studying the process for converting a bread wafer into the flesh and body of Christ probably has like future utility. So
See, it's
if we
it's
could
that
study
kind of
no,
it's
it
that
anything,
kind
doesn't.
of comment that
Come
I
on.
that brought me to you in the first place, Benjamin. But now let's go to
we
CM.
could
Let's go,
we could
let's
study
let CM
anything
let CM get a
under
word in
these
here.
rules.
I mean, so what are you guys talking about? I guess either the validity or usefulness of string theory.
Yeah, I think Jesse's question first was anything about the usefulness or whatever fallout from string theory. I'm not sure Jesse is. And Jesse may can answer this. You may not be aware, Jesse. I think that a lot of people, a lot of important people in string theory, have now pronounced it a failure. So
Yeah,
that's
pretty much. No, no. So we can go back a little bit to like the history, right? The string theory started as like as a way for in the '60s for physicists to try to explain the strong nuclear force. But by the 1980s, Green and Schwartz figured out that well figured out this modern. They figured out that if they added all this stuff, supersymmetric partners and all this stuff, that out of nowhere they would just the graviton, the mystical graviton everybody's searching for, just popped out of the equations and the math of string theory, and that's what led them to think that it was a candidate for this quantum gravity theory or theory of everything.
right.
Um, and then, but yeah, as you said, most physicists have really pronounced it dead in the sense of, well, it's because well, everybody knows there's no confirmable, there's no way to there's no experiments at the moment we can run to actually test string theory. Even the energy, however many giga electron volts or whatever we could produce at the Large Hadron Collider, it's nowhere near enough to actually. So we're smashing particles, and we could get down to quarks and stuff. But in string theory, the idea is that even if you were to zoom in even deeper into the quarks, you would see these little filaments, these little strings vibrating like harmonics, and this is related to quantum field theory. A certain vibrate if it vibrates this way, it's like an electron. If it vibrates a certain way, it's like a notes on a guitar thing. And and but the problem is, again, the size of a string, the theoretical size of a string compared to the size of a quark is so many orders of magnitude that we would essentially need. So this is like the string theorist's defense of when people just brush them off and say, "Oh, you guys can never test your theory, so it's not science and this and
Take
that."
another 30 seconds, CM, and then
Okay,
and I will say a few
they
more things.
they just say. I mean, unfortunately, we would need like a particle accelerator the size of like the solar system to be able to produce the energies required to
The
sufficiently
size.
probe deep into a cork to find a string.
Yeah.
And so that's kind of
Yeah. No, I
that's
think
where they
that's
are.
certainly from that standpoint. I think a lot of the current thinking. I mean, it's not my field, but my sense is that there has been kind of a move, not so much because of it's not so much kind of motivated by the graviton is kind of a central point to think about, right? We've been thinking about that what we need to do to unify the two is to find a quantum theory of gravity that would involve a graviton, et cetera. And I think a lot of the people in those fields have started to kind of think that, like Einstein's looking for a unified field theory, that was just the wrong approach, that there won't be a quantum theory of gravitational fields that creates a graviton, because it's just gravity is a different beast. It's talking about the stage on which things take place. It's not itself a field in the same nature as quantum mechanics. So I think a lot of
Yeah, at the moment.
lot of the kind of moving on has been kind of realizing that it was a failed idea to think that you could just put gravitation in the same kind of a framework as you do electromagnetism and strong and weak force, et cetera.
Absolutely, yeah. The gravitational force is just how weak it is compared to all the other forces. It's just and then also we don't have the quantum description. We only have a classical relativistic description. Um, so yeah, it's term in. I mean, in regards to like the future of string theory and how a lot of physicists, how you said, have like almost pronounced it dead or whatever. I kind of tend to agree. String theory seems like it's going to become more of a branch of mathematics than physics.
Yeah, well, it's stimulated,
Because
as Ben was saying, it stimulated a lot of new
exactly.
ideas in mathematics, right? So that's a good
Tons,
thing.
tons. And they've even, I mean, string theorists have used their wacky math, like unrigorous math, to calculate values of the Riemann zeta function in completely new ways than any other mathematician. I mean, it left mathematicians stunned that these guys were doing this non-rigorous math the way math, like proper mathematicians like I do. They could still calculate zeta of 2, zeta of 3, zeta of 4, zeta of 5, zeta
Well,
of 6.
so see, let me rein you in a little bit. Because we've been over the last 5-10 minutes doing something that I try not to do really in this room. I try to keep this really more a room for non-physicists, for lay people. And I think we're talking about things now that, number one, I don't know very much about, and it's partly why I do what I do with this room. Um, but mainly just that. It's just that I try to kind of talk about things at a level that I can bring non-physicists along
Okay,
and
yeah.
understand
Yeah,
things.
sure.
So I
So I was just saying,
appreciate your contributions, and I hope we'll see more of each other in other rooms. Jesse, I saw you unmute. Did you wanna have another word?
Yeah. I wasn't sure about what the audience was here. I'm like, this first time I joined this room, so and actually I've been active on Clubhouse more recently, so it's a lot of rooms I just started getting active in. So, but
Yeah.
yeah,
Well,
the audience.
I mean, I hope this room today, this whole series, is probably a little bit at the upper end of things that I try to do. But my mantra from the very start has been to not talk about cutting edge physics, to talk about well established physics with a little more rigor than you usually see, in an attempt to kind of show non-physicists, non-scientists, some of the real beauty of kind of the scientific method and things that we do. Sometimes at the the talks that are often given about string theory and this and that, particles, Higgs boson, and all that, are really exciting and all, but when they're given to a lay audience, they're necessarily stripped completely of the details, the mathematical details, and they can leave the impression that all physicists are doing is saying, "Hey, wouldn't it be cool if this or that, et cetera." And so I think that by taking well-established physics that we've really known pretty solidly, say for 100 years, we talk about relativity and quantum mechanics, those we've known for 100 years, but talking about them with a little more rigor than you usually see, without making them inaccessible, my hope, the hope of this room, the people who do talks in this room, Sam Tomasabi in chemistry, and myself mostly, but anybody who cares to do that in their field, we might get some bio talks again. We used to have, is really that talk about rigorous, well-established science that can be presented with a little rigor without losing people who aren't, mathematicians or scientists or whatever. So
Yeah,
hopefully you'll find yourself welcome here.
yeah. Well, I kind of have like a motivated interest in like learning more about what quasi particles are about as well, and the strings, because like I have a vested interest. Well, I've also been corresponding with a polymer physicist who focuses on condensed, soft matter interaction types of work,
I see.
and I'm more focused on the cognitive sciences arena, but I do have an interest in figuring out what's going on with our capacity to have abstract thoughts, like in looking into the whole abiogenesis argument and
Hmm.
what have you. So I do have those areas of interests as well, and it seems like there might be some intersections here. So
Well, let me mention one. If you don't know it, Shamash here, also known as Logic Guy, does rooms not in this house, but in his own Philosophy Wednesdays house, which are
oh,
wonderful on the philosophy of science. And so I heartily recommend them to you. They start on Wednesdays at the same time this one does, 9:30 West Coast time. I'm thinking you might be a West Coaster because you were also on your first cup
I'm
of
in East
coffee.
Coast.
Oh, wow. Well, you wouldn't. Then you got up late, man. If you're just on your first cup of coffee, weren't you the
No, I'm
coffee
not.
guy?
I'm not. I've been up since 8 in the
Oh, maybe it
morning.
was somebody else. I don't know. Somebody was on their first cup of coffee. Maybe it
I'm
was.
curious because it says in your profile you're a retired professor of physics, but I guess what was your area of focus?
So that's the fun thing is that I was kind of an unusual guy in that I ended up teaching at a university at Cal Poly Pomona, which was a California State University, in a physics department headed by a guy who I did most of my work with, who allowed me to be a generalist. I kind of considered myself a generalist. My work was publishing papers in educational oriented journals like American Journal of Physics, which I edited for a year, the physics teacher, things like this. And so it allowed me, but both because our department had a fairly large number of physics majors, I could teach courses at all courses at the undergraduate level, and then publish papers on the kinds of things that I like to do in this room. So I was kind of a jack of all trades, master of few. I'm pretty good general relativity. I'm really good special relativity. I probably know special relativity as well as anybody in the world, but general relativity not so much, but pretty well, and then a few other things as well. But I don't really have there's no field in which I published anything that would even look like cutting edge research. And most physics professors don't get tenure operating like that. So I was a very lucky guy.
Yeah, it's been a blast, and I guess I'll look forward to Shamash's discussions as well. But if there's anybody else you could recommend on Clubhouse to have more conversations about cutting edge stuff,
Yeah,
uh,
well, cutting edge stuff. If you want that, there used to be. Let's see, who is it? Uh, uh,
There's the
Cecilia.
photonics room, quantum
What is it?
photonics.
The photonics. That's what I was thinking of. Isn't that
oh
what's?
yeah, of
Yeah,
course, yeah.
yeah.
Yeah, they still have rooms.
That's a good room if you're looking for that. And also, Doctor, what's his name? Oh, now Andy, you know what I'm talking about. I think you're in his room all the time.
I was gonna say, yeah, that's our room, quantum photonics. Yeah, it's still going strong, and yeah, I was the one on the first cup of coffee earlier.
Oh, okay, yeah. I had that mixed up. Also, I'll just mention Sam Tomasabi does chemistry rooms. I think maybe starting 11 a.m. Pacific time. We had a little. I'm not sure exactly, but he does them in the same house. If you're not a member of the house, cash in your pink ticket. get notified. But we have Monday shows. Typically, he's not quite as regular as Shamash and I are, but Shamash does pretty much every Wednesday, and I do pretty much every Friday. Philosophy on Wednesday, and physics on Friday, and chemistry on Monday. And we're always looking for more things. I'm going to start winding this down. Go ahead, Jesse, but I am going to start winding down.
Yeah, I was going to say thanks so much for your time and having this presentation.
All right. Yeah, you're welcome. Good to meet you, and hope we see you again. Anybody else before we play ourselves out here? Hearing no takers, maybe we will. Yeah, Kevin, go ahead.
I was just gonna say no. Yeah, I don't know if that's on your profile, but yeah, Cal Poly. Oh my God, yeah, I love both campuses. Yeah, I'm in California as well. I'm trying to get to Berkeley.
Oh, good.
For
well, yeah, that's right. So you are. I knew that whoever said they were on their first cup of coffee, I figured they must be a West Coast guy. So I guess that is you.
Yeah. I'm trying to transfer it. Hopefully, I get to Berkeley for bio. I changed my major to bio. Bio.
Well, I went
mechanics.
to Berkeley as a graduate student. That's a great place. Great place to be for a while, and then you kind of feel like you really need to get out, at least to the North Bay, like Andy. Go ahead, Andy.
Hey, I just want to, since I consider myself a northerner now, there are actually 3 Cal Polys. Humboldt is now
that's
Cal
right.
Poly.
That's
so
right.
don't just say both of them. I don't know what it takes to become a Cal Poly, but apparently Humboldt did it.
I really don't. I've never understood what distinguished Cal Poly Pomona from any other Cal State that has engineering. That's kind of technically, I guess, the idea, but it's pretty weird. Yeah, so now Humboldt is Cal Poly Humboldt, I guess. The thing I liked about most people think of San Luis Obispo when they think about Cal Poly. And that really is, in some sense, the jewel of the Cal State system. But I always thought we had one thing better than them. Because their name is California Polytechnic State University. Cal Poly Pomona is called California State Polytechnic University. And I just think that flows better. I just think it's much better to be California State Polytechnic University than California Polytechnic State University. It just doesn't flow.
There's a grammar rule for that. No, they used to teach us this.
Yeah, that's right. And don't you think the grammar rule favors Pomona? I think so.
I don't know. I'm not a native speaker. This is my 3rd language. I have no idea. I don't care, actually.
John, does Pomona get a little cred just from its proximity to Caltech?
It's funny you say that because what was it? I used to do book reviews for Computers and Physics. I used to be the book review editor, and was it that? I can't remember. Well, I think it was in that situation and in others. I got a lot of mail from people and a lot of freebies from people that would write to me, California Institute of Technology, 3801 West Temple Boulevard, Pomona, California. So they would clearly think they were sending things to Caltech, but they would get my address right anyway. So I think that did help.
You don't have to correct everybody.
Yeah, that's right. I just let them, didn't disabuse them of that. All right. Well, thanks everybody for coming. And we will continue, maybe finish next week, probably 2 more weeks on this. And we will see.